Hi, we are back to lecture clip number 21. Okay, in this part we will continue to explore the implementation of vendor decomposition. Okay, to solve this system of mixed integer linear programming from equation 7, 8, 9 and inequality 10, 11 and integer restriction 12. Okay, certainly we already explained that we can apply the similar method in case that when the fixed charge is not considered in the model here. But with the addition of the fixed charge, okay, to the cost model, resulting to a more difficult of the vendor optimality cut model, because it become the problem of mixed integer programming. Okay, and last time we illustrate the computation for one iteration using the Excel platform. Okay, and by extending our problem from the case where there exists only variable cost, okay, and we didn't finish solving the problem from the Excel part. Okay, I leave it up for you, for those of you who familiar with using the Excel macro and Visual Basic, okay, to develop solving that problem iteratively to get the optimum solution. But today we're gonna show you how do we implement the Matlab, okay, environment for solving this problem using the procedure that we already discussed. Okay, this actually this part of the paper is a thing that similar. Try to explain the. If you're familiar with the notation a little bit, you know that this is the same special purpose algorithm to solve the subproblem to obtain the optimum dual solution to create the coefficients of the optimality cut model. Okay, so we gonna go to explain you the Matlab code. Okay, the three code that I developed for you, okay, actually extended and modified from the previous code that considering only the variable cost. Okay, the first one we call it's here, I'm going to explain around this platform. Okay, so because you can expand it. Okay, this is the code to solve. Oh, this one is already a big one. We make a wrong. Okay, let's start with this one first. Okay, test coding fixed charge. Okay, this is the one that we didn't do in the Excel format. In the Excel format, last time I encourage all of you to apply the open solver to solve the original model. Okay, directly, not using the vendor decomposition, and then you can compare the performance of using the direct method as compared to vendor. Okay, but this one in the Excel, the first program of test coding fixed charge available in the folder of lecture 2. Okay, I already import all the necessary data here. Okay, from the Excel file, sorry, the vendor. Okay, and but I did add this one. This is a setup cost. Okay, just put this line. Actually, the program is almost the same as the previous one. This one, the test coding vendor. Okay, you might remember test coding vendor is direct to solve the non-fixed charge problem. Okay, so I just modify this program, okay, and use this one, okay, by adding this line. okay, the setup cost data. Okay, with additional of setup cost data, I need to make sure that the cost element here, okay, instead of just importing only the variable cost, okay, period by period, okay, C1 to CT, I need to extend the dimension of C here to 2 times T, because I need an additional installation for the to store the setup cost here. Okay, and now this is the H range, okay, to import the data from for I plus, and this one for I minus. This is like the O1, and certainly the D, and also the AEQ, okay, and you know that the number of variables need to be extended. Okay, actually D here is not quite necessarily here. You can erase it. I think that it got caught up with the previous modification rule. But AEQ here, the difference from that is that you need to add to the old model. Okay, you have only T plus the number of column T plus 2 times T times S. But the new one, you need to add 2 times T, because you need to add more column for the 0, 1 variable, okay, of P sub T. You might remember from the model. Okay, and also for the F, okay, F lower bound, okay, all this T need to change to 2 times T. Okay, the B range, okay, this is the same. Okay, you just import, and this one we just import and place into the equation constraint. Okay, you have to know that, okay, when you let's look at the model, okay, that we're trying to solve here in the paper of Apisak here. Okay. When you're trying to solve this model, okay, you can see that there's an extra T variable according to P sub T. So when you solve this directly, you need to add more T additional column to your equation matrix here. And also in Matlab, you need to input what we call the inequality separately from the equation here. So you need to add this additional constraint as inequalities. And in the Matlab format, they only accept the less than or equal form. So the metric that generate for this constraint have to be start with inequality, say x sub t minus m times p sub t less than or equal to 0. Okay, so this is the additional direct model you need to add it here. And also we cannot use linplug to solve it directly anymore, because you have some mixed integer requirement for some variable, okay, especially for P sub t here. Okay, so we go and look at here that, okay, so it's just as a regular way, okay, this is all the same here, except that, okay, you have to make sure this is also pretty one thing that's different is that we need to add 2 times t here, okay, for all additional column t additional column according to P sub t. This is, if you look at the old program from when you not consider a fixed chart, this become only plus t. No, there's no 2 times here. Okay, so this one is actually the same here. Okay, and also the cost function here. Okay, the cost coefficient you need to extend to 2 times t column also. Okay, so this is set up the part for the, and this is the additional one that you need a inequality. AIEQ is the submetric for inequality here, which there are certainly only t row, okay, t row, but the number of column, this is you have to make sure number of column also hover with the case when I plus and I minus, even though the coefficient of I plus I minus are all 0 within these inequalities. Okay, and certainly you know that in for AIEQ, AII for row I column I, so this is according to the coefficient of x sub t, and this is the coefficient of minus m, you remember that, and m set up to be a large positive value, Okay, this by minus m is x sub t minus m times y p sub t less than or equal to 0. So this one is set up for the inequalities. Okay, and we are using what we call the integer linear programming object here to solve it. Okay, Matlab have the int lin prop. Okay, when you add int, okay, to the command, okay, lin prop, it become, you can control that if there exists some variable you want to control it to be just the integer result, you can do it by using this. Okay, and this is the way to do it. Okay, first of all, I need to identify the integer constraint here. This command tell you like this. Okay, from the variable t plus 1 to variable to t, okay, in the model. Okay, I want this to have an integer constraint. Okay, integer constraint. It means that variable from t plus 1 to variable 2 times t, which we already know that this one is additional one, right? The previous one, you have the first t variable is x sub 1 t, x sub 2 t to x sub capital T, okay, here. But once this model, you add p sub t in the model. So p sub t also t equal 1 to capital T. So this is where the p sub t is. And you want to add this as an integer constraint, which means that you control that the variable belong to this column, okay, okay, from in the sequence, okay, from t plus 1, okay, to 2 times capital T here, are restricted to be integer. Okay, I'm going to say that FUB is the upper limit. Okay, upper limit of this is the total number of variable in the model. Okay, it's a column vector. This is number of rows, so there's only one column. INF is infinity. Is they will assign a very large number here. So it means that the upper limit for all decision variable is infinity. But then the next statement, I just control them. FUB from t plus 1 to 2 times t, which is the same here. Which already, we add this command to control that the variable within, start from t plus 1 to the variable number 2 times capital T have to be integer value. But I set up the upper limit here, okay? The upper limit of that variable from x, from variable in the order of t plus 1 to the 2 times t, the upper limit is only 1. So this one is to set and control that the variable of p sub t here within this model is restricted to be integer, and the upper limit is 1. Therefore, it can be either 0 or 1. Okay. So this is the additional one that add from the previous program that you can solve the direct method for this problem. Okay, and also the definition of setup cost here, and it is an extra storage, okay, of SC, okay, of setup cost. Okay, and also in the setup of the metric here, okay, you need to expand column, add additional t column here. Instead of only t, it become 2 times t. Okay, so that, and also with the cost of the I plus and I minus cost also, this one has to be expanded to 2 times t. That's just a shift of location. Okay, and after that we all set up to be able to solve this using integer lin prop. Okay, so this code, okay, was developed just for solving the direct model here. Okay, we solve the direct model here. We solve this direct model also. Here it is. Okay, 7, 8, 9, 10, 11, 12. We're going to solve this directly, and the number of scenario is 1025. Okay, and once you understand the code here, the code was already put it in the Matlab environment here. Okay, the test coding fixed charge. Okay, you can also find the folder 2, folder lecture 2. Okay, so this is the one. Okay, actually I already run some part of it, so okay, this is a number scenario, the number period, and we have an additional set of codes. Actually, this program we already explained. But once we put it in here, we're gonna try to solve it a little bit. Okay. Okay. Well, once with this, we can solve it. Okay. Test coding fixed charge. Okay. Still solving. Actually, have branch and bound and cutting plane, and you might call this algorithm the branch and cut. Will it take forever? No, only 16 seconds. Pretty fast, huh? Actually, this problem have more than 20,000 variables, but there's only, remember, 12 integer restriction of piece of t, because we deal with only 12 period. But still, it's pretty fast, 16 seconds. It doesn't take very long. Okay, so we are back to this part again, that to take a look at implementation of the methodology on the Matlab platform. Now it's time for the vendor for PP production planning control fixed charge, when we have a set of costs added. As this one is for, we're gonna solve exactly the same problem here, okay, but using vendor decomposition. Okay. Certainly we need to adjust a little bit also, that we need to input similar to the test, the direct method software. We need to add this, and we import the necessary data from test vendor.ppc, except the setup cost has been added here. Okay, and you can see that here the number of variable and all of this all together here is not still not updated yet, because it doesn't have anything much to do with the when you're dealing with vendor decomposition, because vendor decomposition will not solve the direct model. They will eliminate all the I plus and I minus variable. So what we really have to change is over here. Now the number of decision variable x after you erase I plus I minus is 2 times n, not just n. The reason, the previous one you have only one n, 1 times n, because you have x sub 1 to x sub t. But now you have x sub 1 to x sub t and p sub 1 to p sub t. While all p sub 1 to p sub t is restricted to be either 0 or 1. Okay? So this is the thing that we need to improve, that your decision variable and related cost coefficient, you need 2 times n, okay, not just n. Okay, and this is still the same, that okay, these 3 lines just like the old program, okay, but we have additional of CV here, that you put the setup cost where it says SCJ come from, SCJ come from here. You just input. I just import the setup cost down here, okay, to solve the problem. Okay, I think that the setup cost down here is a little bit different than what we are doing here in the Excel, if you might remember last, because the setup cost here in the Excel model is this, okay, 2082, which is different from the data in the Matlab here, okay, or you might look at here, our setup cost here is a different value. Therefore, you cannot expect that they gotta get the same results here, unless you change this and redone this problem, start from the first cut again, okay, which is not a big deal, because just just to remind you that there's some different of data input in when you try in one model. So the resulting solution in both of this problem now is not the same. Why? Because when I wrote this Matlab code, and you might remember this setup cost, I just borrow this value from this part, the setup cost here, from the classic paper of Wagner and Richter. Okay, why the old Excel file here of this demonstration we use just as assumed data. Okay, we setup cost 200 something between for all 12 months. Okay, just to remind you so that you're not confused with that. If you continue to solve using that Excel, you're not going to get the same. So unless you change the data to be the same, the setup cost is the same. Okay, so you can see that there's some shift of the variable here. You need 2 times t instead of t, because of you have to reserve more memory to handle the coefficient of piece of t. Okay, this certainly is a cx1 only in the objective function. Is only this one is only 1. I think that I did the reason is 1 here, that this is something different from what we did in the Excel file. Is that for this one, you remember that in Excel we put the original t plus the sum product, and when you compare to the original, to the paper of Apisak here, okay, you can see that actually the summation ETPD, he put it in the optimality cut concept instead of putting this into equation 16. Okay, and I did ask you a little bit, is there any different about this? That's an opening question that you can discuss. Okay, but this one we just follow when we develop the Matlab. We follow the what his proposal here, also in equation 17. Okay, here inequality number 17 here. So the coefficient of setup cost need to put in all Bender cut here. Okay, instead of putting in the objective function. Okay, and that is why the CV here. Okay, we put the setup cost here. Okay, and also the this one is for x, this one is for p, and also there's only cx1 only equal to 1. We didn't put the cx cv here into any cx. Okay, because all this we will put in the coefficient of Bender cut. Okay, so the objective function will be only minimize t in this case, that follow what the same as here, minimize t. Okay, and now we start to count. Okay, icons. Okay, this is the number of constraint. Okay, so we put this before. Okay, this is a requirement that you remember that the cutting constraint here. Okay, there's some inequalities here in the master problem here. You look at equation 18. Okay, here all coefficient of x will be 1. If you keep moving from for all t, it's gonna form by identity matrix. Okay, and when you move mpt to the left hand side, you're gonna have minus m. Okay, and in the submetric as a square metric also, size of the capital T times capital T. Okay, so this is the coefficient along this one that we put it on here. Okay, so the icons here start to counting. Okay, the number of constraints here, and we have the cut constraint here. Okay, and this is a fix. Okay, it will be fixed for every iteration. Okay, so this one is already fixed. It's not, you will not add it, but when you finish it here, this is the way, as I told you before, we put the constraint here first. Okay, and so the AER is a gap between upper bound and lower bound, and then you have an upper bound large positive value, just trying to update and then keep the best solution. And now we're entering the loop of the vendor decomposition here, okay, which is almost quite the same, okay, from the previous program that we do, okay. Certainly in the first step, okay, once you're going to have the cut coefficients, okay, cut coefficient first, okay, and you have a right hand side cut, and all this is almost the same as because this is the routine that we find the optimum dual, and we set up the cut coefficients, okay. By the end of this you get the cut coefficients, and then you can move the cut coefficients here by minus, okay, here. This is what we when you look at the paper here, the cut coefficient here, okay, you need y here, right? When you move this to the left hand side, become when you find the new x is here, right? Okay. Once you get the cut coefficient with summation y here, you need to minus the ct, and when you with the minus sign here, when you move to the left hand side, it becomes the minus. But actually, minus is already correct, because when you put it in the Matlab inequality form, you need to, they allow only use the less than or equal sign. So you need to move the t to this side and put the data into the object in the integer linear programming, okay. Okay. So now, okay, this is why they minus c, okay. Now the constraints start to increase, the new cut, okay. But you have to know that now icon didn't start from 0, because icon start from t, okay. Because before entering the loop, okay, they already set up the constraint, established the relation, the coefficient that related between the x sub t and p sub t. Okay, and so this is almost the same as the previous program. We have the cut con here, and then the cut con is you need the -1 in the first, because you move t to the left hand side. Okay, then cut coefficient is all here. Okay, all cut coefficient is here. The coefficient that multiply to for each x sub t, for all t. Okay, and now you can see I need to identify the lower bound here, start from 0, and the upper bound I declare as an infinity value. But now your decision variable is 2 times t plus 1, right? You need to add additional t variable according to p sub t, and the cut con is the same, okay, right here, the cut coefficient here. But okay, this is the t, or the optimum here. Okay. Okay, we go on to take a look at this line. This is the upper limit. Okay. As the upper bound is the default, is that this is similar to what we did in the test coding fixed charge, that you give the infinity upper bound for all major. This one not included the I plus I minus, just the remaining variable. But the upper bound of t plus 2 for 2 times t plus 1. This is not t plus 1, right? Because remember that you have the first variable as a t variable in the vendor or the optimality cut. So this one has to be shifted by 1 position. The upper bound for this, for p sub t, are all equal to 1. And this is an integer constraint for this. Okay, and certainly the right hand side, you just, okay, minus the right hand side, okay, down here. Okay, and you know that this is and after that you get solved for the solution, you get the new x, okay, but the new x now you have 2 times t, okay, remember that. You have both x sub t and p sub t from solving this one. You have integer constraint, put it in here. This is a new abbreviation, what do you call the attribute, okay, that add to this object, okay, when len block don't have this, but integer constraint you identify here. And this is a cut constraint, the right hand side you have lower bound and you have upper bound, okay, and you want to solve this to the optimal solution. And then this one is after you get the solution, you compute I plus I minus, and then now you can have this one I plus and UV cross, and then you CV times X here. You remember that this always cover both the production cost per unit, okay, for each period, and also the setup cost. If you place an order in that period, you need to add a setup cost according to that month data of setup cost. Okay, so this one is already add. It means that just modify the old program by adding up all the constraint about here. Okay, this one is also the additional one we need to add, because for every cut constraint coefficient from t plus 2 to time t plus 1, you need to add the setup cost coefficient here to refer to this. This one is coming from here. When you put the setup cost as a cost coefficient, okay, for all vendor cut here, okay, therefore you need to put this value setup cost as a cut constraint coefficient for the j location, and j is a variable from t plus 2 to time t plus 1, which is the all variable related to p sub t. Okay, and then you reverse the sign of cut con because you move to to make it less than or equal inequalities. Okay, so this one is an extra one, so you need to add. So now we already simulate what we are doing here, okay, with 16 to 19 here, to set it all up to be ready to put and use this one, integer linear programming here. And once you get the solution, they update, okay, fine, check whether they get the better solution. If they get a better solution, they replace all the solution in X OPT, and then find the range, the gap, duality gap between upper bound and the lower bound, which is the C here. Okay, so the upper bound. If if the loop start to restart it again if you haven't reached the convergence tolerance yet. Okay, so this is what we did here, okay, for the Matlab code. Okay, we're gonna compare trying to run this problem as compared to running the direct model. You remember the direct model we run previously? It took 16 seconds, but this one is the same one that we use over here. We're gonna check the solution a little bit, okay. From the test coding fixtures, okay, the optimal solution is kept here in Y, okay, the total objective function. Oh, sorry, where did I put it? Okay, okay, I need to put it in. Okay, what is the value of Y? It's around 11,056 something, okay. This is the optimum solution from solving this, okay. And we use the Excel file, but except that the setup cost is a little bit different, okay. Where is the setup cost? I think the one line was lost. It's setup cost here. I don't know where I need to bring that data back again. Okay. Actually, you have a setup cost down here. This is a setup cost. Okay, you need to copy. And actually this fixtures, okay, you have this, okay, you need a setup cost. So I think I'm going to rerun this again, so I can make sure that it's got the same result. Okay, test coding, fixed charge. Could be 16 seconds again, or 17 or more than that. Okay, 16 seconds again. So actually when we run it, somehow this line lost previously, and I need to put it back in. So what is the value of y? The objective, it's the same. Okay, and what if you want to know the lot sizing? Okay, you have to make sure that now the optimal solution was kept in P. But if you print all the P, okay, there will be more than 10,000, 20,000 related variable, because the direct model already include both I plus and I minus. So you have to know that when we set up this problem, we make sure that only the first 2 times t variable is related to x of t and p sub t. So I'm going to print the optimum solution here. P start from the first variable to 2 times t variable only, not all the p. Just make transpose to make it readable line by line. So this is the optimum lot sizing plan. Okay, for 12 period. Okay, here this 12 period. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the first period you place an order 150, 70. Okay, for 2 period. Okay, and then you third period, this is how much you place, and then in the 5th period, 5, 6, 7, and then in the 8th period, okay, and the 10th period. Okay, here this is the optimal solution. And you can't say that you place order when inventory is 0, just like what we discussed in the Wagner-Wittin. Okay, because with the different pattern of demand, you will see that the next lot size, the next order placement, in some scenario there still exists some either I plus or I minus in the system. Okay, but this one just to evaluate the total expected deterministic cost plus probabilistic cost all together to be minimized. And you can see that the relationship, this is the first 12 result. Okay, and this is the integer variable here. Okay, the 0, 1 variable. You can see that when 170 related to this one, because this one you place an order 0, but the second period you didn't place any order, so no, there's no setup. The third period you set up, so another one here. Okay. When you multiply to the cost relative, it becomes the setup cost that we added, and then okay, the next one is 0, so there's no setup. Okay, for 226, okay, another setup 1 here, and then you have 2 consecutive periods with no placement, so no setup, and then with 126 here, okay, another setup here, okay, and then you 166 here, okay, 166 first, okay, related to here, okay, 166 here, okay, and then you don't have any setup here, okay, no setup, and 126 related to here, this setup, and then the last 2 period, 11, 12, no setup. Okay, so we're gonna keep this result here, okay, to compare that, okay, from this test coding, because this is a vendor fixed charge from our example. Okay, as I already explained all the logic of the program development for you. So in the next step, okay, we're gonna run this program. Okay, we're gonna test. Oh no, not test coding fixed charge. Oh, sorry, repeat it again. Oh, come on. Another 6 seconds. I forgot we need this. We need to run this program. Okay, go on and we wait for a while. Okay, doesn't take long. 16 seconds. Okay, we're gonna run this bender. Okay, we have to make sure that because the result will be clear, so we're going to print it out again, y, and the p 1 to 2 times t. Okay, so this is the solution from the direct model. Okay, And then when you solve this Bender fixed charge down here, okay. Oh, it's keep running. Oh, so it's gonna erase, replace the data previously we found, okay. But you might can still remember. I think we can check it out. You can see that it take longer time. Huh? You might say, oh, Bender, poor Bender, now they're being beat by solving the direct method already. Okay, which certainly is okay because it's it took. You might remember from our previous work that we did that when you didn't have much number of scenario, okay, normally Bender not work better than you solve the direct model. But when you solve the direct model, as the number of scenarios start increasing, okay, at one point you're going to end up cannot solve the problem. But again, this example will show you that Bender can still hold on for a large number of scenarios. Okay, it take a while. Okay, this is a Bender cut. Okay, every time, and you know every time now they didn't solve it as a linear programming. They solve it now take around 1.5 minutes, 82 seconds. You might say, oh, the previous one you remember only 16 seconds when you solve directly here. But Bender took 82 seconds. A lot of we're gonna check the results here. Okay, the results here, the optimum solution is keep in the upper bound variable here. You remember that 1.1056? Remember this number a little bit? I'm not sure they keep probably run long enough. So okay, you cannot trace back and look at the previous example using that. But we can rerun it again to check. Okay, this is the upper bound, and we're going to check the optimal solution here. Okay. Oh, we do it x upper bound, and we're going to do x optimal as transpose. Okay. Does it look familiar? 117. Have you seen this before? Have you seen this? I think this is a solution that we found in when we use the test code in the direct solving the direct method, and also this is also the same optimal solution. One observation that you can look is that we didn't when we solved this problem, we didn't put the restriction on the x variable here that it had to be integer. Okay, but we only put the restriction on only the p sub t here, the 0, 1 variable here. Okay, when if you might look back at the program at the integer constraint here, this command, and with the and also the upper limit here. Okay, that these two lines that's control. So you might wonder that is this solution, and if you might remember when we working on the Excel file, the solution that we found so far in the first couple of iteration doesn't look like an integer at all, except the first one here. Okay, but in Matlab here, the solution, the final solution come out is it automatically become integer, or it just by lucky case in this case? Okay, that's another mathematical proof, and for this property is an interesting theoretical problem anyway. Okay, and which condition that your result will be automatically become integer when you can relax those constraints. Okay, and automatic give you an integer. In this case, it does here. Okay, this is the optimal solution, and you might say that I'm going to run it again here. Okay, it doesn't take that long, only 16 seconds. Okay, if I run test coding fixed charge again, okay, so get this one. Okay, here it comes, 16 seconds, right? You wait for a little bit. Okay, only 16 seconds. Now you know that the optimum solution, if you might remember, is store in y. This is the objective function. Oh, I always forgot this. Okay, we need to put the cursor here. Okay, the y, you remember 1.056? Go back and take a look at the result that we found here. Look at the same. This is the upper bound from the Bender decomposition. And x optimal solution, okay, from when you solve the direct model, you only want to look at p from the first one to 2 times t. Okay, and you want to transpose it. Yeah, this is the optimal solution. And you can check that without looking back, you know that it's the same one. Keep the same optimal solution. Okay, so it's all set that to test the validity of two approach, solving directly or using the Bender decomp. But the thing that got caught in your mind is that the total time consumed. In this case, you must remember that we test on the 1025 scenario. The fixed charge here took the test coding fixed charge directly, solving the model directly. Get the result only 16 seconds. Okay, now this machine is not. I'm recording this part in my office, so this one is around I core 5, I core 7, so it's much faster than the machine that from last illustration that I did from home. Okay, for fixed charge example, it took 1.5 minutes, if you might remember. But is the behavior of the response of these two approach, it will be similar, the same as we did experiment previously or from the other example, that as you increase the number of scenarios, okay, which you cannot hear because this is a fixed scenario and you already export the data here. So I need to develop another program here we call Bender fixed chart set number scenario here. Okay, and we can go back and look at it's already in here. Okay, that this one. Okay, this is the Bender fixed chart. This is the one that we're gonna try to solve it. I just modify the code from the Bender code for the example to be able to handle as much as number of scenario as much as possible. Okay, I'm not gonna spend too much time to review this. Okay, but it has some similar. Okay, this one also I didn't import directly from the Excel. I just put the data. This is a cost per unit, if you might remember. This is a setup cost, and then what I use from the data from the Excel file is that we need to generate the demand here by using integer. You remember that this one is trying to simulate what we did with the integer rounding. Okay, when we use in the Excel file the int. Okay, this one is a simulation. Okay, the 50 plus. You have to know that the integer command in the Excel is you always round down. Okay, you always round down. So this one is a simulation to generate the demand in a similar fashion. So the demand is not probably not going to follow what those 1025, but is have the same route of generation. Okay, so in this case, you can always increase the number of scenarios as much as you want. In this case, I just put 1 million. Okay, that's a lot anyway. Okay, but and that's all what we did here. Okay, we rearranged the early part of the program, the input part of the program, so that instead of the Bender that import the data directly from Excel file, they be able to generate as much as number of scenarios as they want. Okay, so that's the logic of this program. For the remaining part, once you set up the initial setup, okay, follow the same thing that what we did in the previous program, in the solving example here. Okay, so we're gonna try to run this program for you. Okay, this one is a third program here. Okay, we just everything the same, but we're gonna try to make it a small scale, maybe 10,000, which is already, if the relative number of variables is already more than 24,000 variable already. Okay, so we're gonna solve this one. Okay, instead of it's gonna run, keep going. Every time you remember that in LP they only show the optimal solution file, but when you use integer linear programming, they will show you the proof of optimalities, okay, for the integer restriction, and also show the progress of approaching between upper bound and lower bound. Okay, we're going to see how long does it take for 10,000. Is it longer than you remember that we in case of 1,000 scenario, okay, we took about 1.5 minutes. Okay, but this one is 10,000. Okay, it will probably take longer time. Okay, but again, for this one I encourage you, we can arrange this program and make it for the test coding. Okay, adjust the input process here for the test coding, so you can compare that if you solve it directly and when you solve it using Blender. Certainly for a small number of scenario in the 1,000 unit. Okay, you solve directly, it should be faster. Okay, but the rate of the time increasing, we have a steeper slope. Okay, as the number of scenario increase. Okay, why for Blender? Oh, this one not bad. Still 80 seconds something. Not that far from the case of 1,000. Surprisingly, remember that we solved the 1,000 here. It took around 1.5 minutes. Okay. This one, when you increase 10 times, almost 10 times, 9 times something. Okay, from 1025 to 10,000, it took only 87 seconds. Okay, so not that bad. Okay, so we're gonna take a look at the upper bound here. So remember that the previous one we get 1.015 or something. So this one is start to be fluctuate, but pretty close to the same amount. And we might take a look at the x optimum here in this case. Okay, a little bit different. Okay, but in the location of the place, all the placement is exactly the same, but the mouse is a little bit differentiated. So what does this mean? This means that with the increment of the number of scenarios, the solution is still not reaching the steady state result yet. Okay, so what you need to do, you need to add more. Okay, you might run for 100,000 and even 1,000 scenarios. I did run 1 million scenario. Okay, but it took longer time, and you can go ahead and do it on your own computer. Okay, and it took maybe around 10 within 15 minutes, okay, in the computer in my home. But if I'm using this computer, it might be faster. Should be faster. Okay, but I use when Core i3, okay, back home is took maybe less than 15 minutes. Okay, but if you and I can tell you, I also increased the time to 15 with additional data here of both production cost and setup cost, with a 1 million scenario, and ran it on my computer back home. So it took 3.5 hours, 3 hours 25 minutes. Okay, so you can see that when size of the problem start to increase, and the response of the program start reaching the limit, the uncomfort zone of response. Okay, it means that you start taking too much memory, main memory, okay, and all of that. Okay, but certainly all of this can change when you improve your the efficiency of your hardware. Okay, and I think that for the fixed charge problem, according to paper of Pisak here, okay, I come to the conclusion here that we can implement his idea here on the Matlab, or either on the Excel we give you as a start. If you can be able to write Excel macro, you can go, and it'd be interesting to do comparison between both platforms, the advantage or disadvantage. Okay, and this one for the program. This one is the way that we already did. Okay, and we might take a look at the results. Okay, toward the end that when he used this to solve the problem. This one, even in the case of the number of scenarios, this is using the direct mixed integer linear programming, just like what we did in the test coding code. And BCS is the algorithm that he implemented. Okay, and this is the size of the problem. Okay, in term. Okay, in our problem, I think from the table, when you plot it, okay, you will see that this is the just consider with the Bender decomposition here approach here with special method for the solving subproblem. It looks like a linear, still doesn't have showing the quadratic or even the higher polynomial or even exponential behavior. You should know why that we even when we add the integer restriction here, okay, to the problem when fixed charge or setup cost is added to the model. Okay, we didn't check one of the value that we should do. Okay, this one, when we solve this problem, you might be interested to take a look at the value of icons. Okay, you remember icons? This one 268, but you have to minus 12 here. You remember that the initial icon before the Bender loop, they count the constraint here of this one, this one, and the equation inequality 18 here. Okay, they initiate this inequality 18. Okay, so when you solve it, the start icon not start counting from 0. So you already have 12 inequalities before. So the number of Bender loop iteration is only 268 minus 12. So it's going to be 256. Okay, 256. Okay, and if you might remember that when we didn't consider the fixed charge, the number of Bender cut is 200 something also. But this one increased a little bit. Okay, that's 200 earlier, 210, 220 or something from in case of with no fixed charge. Okay, and if you take a look at this program, the Bender fixed charge here, okay, you can see if I run it again, okay, remember that this is a 268 is from when you have a 10,000 scenario. Okay, from this program. Okay, now we're going back to the 1,000 case here, and we run it again. Okay, wait for 1.5 minutes. Okay, wait for a little bit. You know that it's 82, right? If I can still remember. And remember that for 10,000 cases, it's also 80 something second also. Okay, so from 1,000 to 10,000, it's meaning that the program still respond in the comfort zone of your hardware. Okay, and coming out already. When you run this problem, you have to be patient a little bit. It's getting longer and longer. It doesn't look good for me. What's wrong with it? Should come out already. Oh, okay, 82 seconds. Okay, remember that for this case, 10,000 we solve 87 seconds, but for 10,000 we're gonna look at the icons here. This is also the, and you have to know that the icon is 263. Remember that for this one, 10,000 you have 268. So the number of Bender cut doesn't change much. Okay, when your scenario increase. Okay. That is the secret behind the success of vendor decomposition. While you solve the direct model, okay, once the scenario increase, your time, your consume time of processing increase in a steeper, okay, rate as compared to you using the vendor code. Okay. So certainly I cannot do it all for you, but this one just getting start for you. You are interested, you can modify all this program and conduct your own experiment to see more of a system response or behavior of the algorithm as compared to using the current commercial software. Okay, so okay, we are done from this part. Okay, but next time we gonna go back to wraps up some other part. No, it's not the end yet. Okay, there's still some other part in lecture 2 folder here that we need to mention and continue. Okay, learning. Okay, so from this part, okay, it's end now. Okay, see you in the next part.